Hello everybody and welcome back to Maths. Hope you're all doing well, and today we are doing some exercises to practice what we learned previously about stacks and linked lists. Before you watch this, please keep in mind that I made a correction video to the last one where I made a bit of an error in terms of how to actually implement stacks with linked lists. So please go back and watch that because we're going to be using the correct version, thankfully, for this video. Also, we will be practicing some concepts that we learned regarding runtime, so big O of 1, big O of n runtime. So if you don't know what any of these are, maybe go back and watch the video first, and then once you have that, you're free to come and practice. So on the screen, I will be flashing out the problems. As always, pause the video, try the problems first, and then you can watch the solutions. Question 1. Okay, so for this first question, we're asked to use a linked list as a stack, show what each of the following operations do to the stack. So we have kind of these stack operations here where we're pushing some data onto the stack, then we'll pop some data, and then we'll push again. And we essentially want to show what that looks like in terms of drawing kind of a linked list diagram at each step in the process. So when we push a 3, what does it look like? Then we push a 4, now what does the linked list look like? And so on and so forth. For this one, we're going to start with pushing a 3. Alright, so what we do is we kind of create a storage spot in memory, 471 let's call it, and it's got inside of it 3 as its data. And we will label this as the top of our stack. Alright, so that's simple enough, right? Just one piece of data, we're good to go. Now for the next piece of data, we're going to push a 4. Alright, so we have the 3 from before. And now we're adding a 4, and again we can kind of put whatever we want for the storage address. And in order to link this 3 and 4 together in the stack to kind of create an order, what we need to do is we need to add a pointer to this to make it point to the previous top of the stack, right? So this 4 needs to be pointing to the 3, so we add in the memory address where the 3 is. And what that's going to do is it's going to essentially link these data together, right? What we need to do now is we change the label, right? So now instead of the 3 being the top, now the 4 is our new top, right? So we've added this to the top of the stack. So now what's next? Next up is adding an 8. So we're going to push 8 onto the stack, and it's going to be the exact same sort of process, right? So we just draw our 3 pieces of data. Okay, so this part right here is the same as before, right? And now we're adding an 8, which we're going to put in memory storage 691. And in order to link them, we need to have 8 point to where the memory address of the 4 is, or the previous top of the stack is, right? So to kind of add to the top, you need to have it point to the previous top. So we're going to have 8 reference the 2210, and that will create a pointer which will effectively link our new data into the stack. And we change the label to where we have our new top here. So we've pushed 3, we've pushed 4, we've pushed 8. Now we need to pop twice. So let's do one pop. So the first thing we need to do is we need to put the top to where it was previously, right? So we move the label of the top down to the second part of the stack because that's going to be our new top. And then we're going to get rid of this 2210, this memory storage pointer, that will dissolve this arrow, and then, well, we can do whatever we want with this data, but it's not going to be there anymore, right? So effectively what we end up getting is just basically a copy of what we had before we pushed 8. All right, just like that. And then we're asked to pop a second time, right? So when we pop again, well, that'll take us to what we had before, because again, we're moving the top label to the second spot now, and we're removing this memory address, which is going to disconnect this previous top from our stack, which will then leave this as what we have in our stack. Okay, so that just leaves us with this last piece of data in our stack, right? So we popped, so now this isn't in our stack anymore, right? And this is our new top. And lastly, we're asked to push 1 onto the stack. So we have our stack from the previous step, which is just this 3 in storage spot 471. And now we're wanting to add a 1 to the stack, which will be in some other storage slot. But in order to make this 1 point to the previous top of the stack, we make it point to storage spot 471, which will give us the pointer there. And we relabel, so now this is our new top. Okay, so this is what every single step of this process looks like. All right, so let's try part B, which is the same kind of thing, but for different values. So for this one, we're asked to push bow, then maths, then pop once, and then push 69. So remember, it's not just numbers that are data, right? It can also be, well, words or letters and stuff like that, right? So these also count as pieces of data. All right, so let's just go ahead and follow the same sort of process. So the first thing we want to do is we want to push the word bow onto our stack. So that creates kind of a single piece of data, and that's going to be at some sort of memory storage slot. So that's the first step, pretty easy. Next up, we want to add to this stack, right, by pushing the word maths onto the stack. All right, so we have what the stack looked like previously, which is bow, and now we're adding maths. And again, we can just make up whatever the memory address we want. Let's go with 708. All right, so for these to be connected, we need maths to point to memory address 420, and that will link these two together. And this will be our new top. And I forgot to add that this is the top in the previous step. Okay, so next up, we want to pop once. So popping once, what that's going to do is it's going to basically undo what we just did, right? So it's going to get rid of this 420, which will get rid of this arrow which connects them, right? So it won't be linked to the stack anymore. And we're going to also rename what we had before to the top of the stack. And so that just takes us back to where we started, right? Okay, and then the last step we have is to push the number 69 onto the stack. So words are data that we can manipulate, and so are numbers. Okay, so we have our new data, 69, which is in storage slot 51,201, and in order to connect it to the stack, we need to make it point to storage spot 420, which is where the top of our stack is. So now we relabel the top to be over here, and bada bing bada boom, that is our final state of the stack after we've done all of these steps, right? And we've kind of seen what the linked list or the stack looks like in between every single step, right? And if you'd like some more practice, please go ahead and push and pop various data items in various orders, right? So choose what you want to add, choose what you want to remove from the stack, and just get practice making kind of the diagrams that we just did.
Question 2.
So for the second question, we want to use a linked list as a stack, just like we did, but now it's for kind of maybe something a little more useful. Instead of just adding and taking away random data that we've made up, we're going to do it to solve this expression here, right, which is in postfix notation. So if you haven't seen my video on postfix notation or my video on how to use stacks to solve postfix notation expressions, please go ahead and watch that. This will be some good practice in order to do that, and we're going to write it out kind of with this linked list. Okay, so just as a quick review, the way we sort of evaluate postfix notation expressions using stacks is we just keep pushing numbers, and then when we hit a operation, so when we get to an operation, we pop twice, evaluate, and then we push the result back onto the stack. So that was kind of our overall process for doing these, for evaluating these expressions with stacks. So our first step is we're going to be pushing a 2 onto the stack. All right, that's our first input. And this is the top of the stack. All right, so just like what we did before. Now we add a 3 into the stack, so we're going to push 3 on. And in order to connect them, we need 3 to have a pointer to memory address 479, and now the 3 is our new top. All right, next up we have another 2 that we're pushing onto the stack. And in order to link that up, it's got to be pointing to memory address 220, which is what the previous top was. And we relabel that to our top. So now we've pushed the 2. All right, now we get interesting because now we are adding the multiplication. And when we add in the multiplication, we have a few things we need to do. We need to pop twice, and evaluate with those numbers and then push the result back on. Okay, so let's start by popping twice. So what we'll end up with is we're going to have the 2 and the 479, right? And that's going to be the top of our stack, right? Because we've sort of taken these two pieces of data out of the stack. So this is the top. And then we have these two pieces of data as well. So notice they have an empty pointer now because they're not pointing to anything because they're not in the stack anymore. But we still have these pieces of data stored at those memory addresses. So we've accessed them by kind of taking them off the stack. And then we're going to perform multiplication on the 3 and the 2. So the 3 times the 2 gives us 6. And then as a result, we're going to want to push this 6 into our stack. So we push 6 by, first of all, 6 is in some sort of spot in memory. And then we just add a pointer from 6 to 479. So that adds it links it into our stack, right? And now this is the only thing in the stack with an arrow not pointing into it, so this is our new top, right? Okay, so now this entire process here, these 3 steps, popping twice, right? So this is 1 step, this is another step. I guess 4 steps because we have to pop twice. We multiply, so then we get 6. And then we push that result back onto the stack, right? So this entire process right here will be performed when we input the multiplication symbol. And next up, we input the subtraction symbol. So once again, we have to pop twice. And since we only have 2 pieces of data in the stack, our stack is actually going to end up being empty, right? We're taking both the pieces of data out of the stack, so this is just empty now. And what we're left with is just kind of 2 pieces of data, and neither of them have pointers to each other, right? So they aren't in the linked list anymore. And then, performing the subtraction on them, we have to do 2 minus 6, which gives us negative 4. And then we're going to push this negative 4 back into the stack. And since it's the only thing in the stack, well, it's kind of automatically our new top, right? And so the top of our stack here, since it's the only number inside, this is our result. So our total result is negative 4, and we computed it how a computer might do it if it was using a stack to go about it. So again, it's a long process, and obviously we could do this much faster, but it's about kind of appreciating how these work. So let's try another example. Okay, so this one's got a few more operations, but it's going to be much the same thing. We're going to start by pushing a minus 5 onto the stack, because that's our first input. And this is the top of the stack. Next up, we're going to push 8, right? That's our next input. So we're going to push 8 onto the stack. Okay, and to link it into the stack, we need to put a pointer to the memory address of the top, which was negative 5. So our memory address is 101012. So now this is linked into our stack, and we can call what we just added our new top. Okay, next up we have multiplication, right? So we are going to evaluate multiplication. So our first step is to pop both the pieces of data that we have in the stack. So that means our stack is going to be currently empty. And then we get these 2 pieces of data that are kind of separate without any pointers or links to each other. All right, great. So now we evaluate the multiplication now that we have access to the minus 5 and the 8. So minus 5 times 8 is negative 40. And then we're going to push negative 40 back onto the stack. And that'll be in a different memory storage spot. Okay, our next step is we're pushing a 10. And at this point, we're probably getting fairly comfortable with this process. Next up, we have to push an 8. All right, so now our stack looks like this. And now we evaluate a minus sign, right? So that's our next input is we input an operation. So when it comes to inputting an operation, we need to pop twice. So the minus is going to be affecting these 2 pieces of data. Okay, so after popping, these 2 pieces of data are no longer linked into the list, so they have no pointers there. And our new top is going to be, well, just the last piece of data in the stack, right? So that is this minus 40 here. So now that we have these two pieces of data sort of free from the stack, we can evaluate them with subtraction. So we do 10 minus 8, which is going to be negative 2. And then we push negative 2 onto our stack. And so now our stack looks like this after we evaluate with the minus sign. And so the last step is with division here. And I've kind of run out of room, so I'm just going to shrink a few things. Okay, so last up, all we need to do is we need to evaluate this division. So once again, we're going to pop twice, and that's going to take out our two remaining pieces of data. So our stack is going to be empty. And we're just going to kind of have these two pieces of data free for our use. Also, I just noticed I made a slight mistake. When we do 10 minus 8, we should be getting plus 2, not minus 2. So this should be plus 2 here. So then, yeah, we just get regular 2 there, not minus. My bad. They have no pointers, right, because they're not in the stack anymore. And then when we do negative 40 divided by 2, we get negative 20, right? Negative divided by positive is a negative. And then we're going to push this negative 20 back onto the stack. And we have no more inputs, and we have just one piece of data in the stack, so our result is minus 20. Right, so again, big process, but your computer is obviously really fast, so it does this really fast. But it's kind of cool to visualize this. So if you want any practice with that, create your own postfix notation expressions like I did, and then evaluate them using a linked list as a stack, just like we just did.
Question 3.
Okay, so for this third question, we want to see if the following operations run in big O of 1 or big O of n time. Remember, with big O of 1 and big O of n, these were kind of ways to look at how many operations occur based on the amount of data you have. So with big O of 1, no matter how much data you have, it's always the same kind of fixed amount of steps every time. So if you're dealing with 20 pieces of data versus 7 million pieces of data, maybe you still only do the same 3 steps. But with big O of n, that relies sort of on how much data you have. So for example, if you had 5 pieces of data, then maybe you need to do 5 things. But if you had 7,000 pieces of data, maybe you'd need to do 7,000 things, right? So it kind of increases the amount of operations you have to do based on the amount of data that you're inputting. So we're going to look at different operations and see if they occur in big O of 1 or big O of n time. So for the first one here, we're given a collection of numbers, and the operation is dividing them all by 2. So for each number we have, maybe it's 10, 8, and negative 3, we have to divide them by 2. So the process would be, okay, we take the 10 divided by 2, and we get a 5. Take the 8 divided by 2, we get a 4. Take the negative 3 divided by 2, and we get negative 1.5. Okay, what if I did the same thing, but to this list? Take the 7 divided by 2, I get 3.5. 10 divided by 2 is 5. 100 divided by 2 is 50. And 120 divided by 2 is 60. So how many different things did I do in this first case? Well, I did 3 different steps, right? 1 for each of the data I had. In the second case, I did 4 operations, right? 1 for each of the data I had. So basically, the more data I have, the more operations I have to do, because I have to, every single number that I have to divide it by 2, right? So that means this relies on how many inputs we have or how much data we have, which means this is going to be big O of n time to do this operation. For part B, it says, okay, the operation we're looking at now is obtaining the piece of data that is second to the top of the stack. Okay, so we've got some stack, right? And this is the top of our stack. So all we need to do is access the second piece of data. So we can do that by popping off the top of the stack, and then we can access what is below because this will be our new top, right? But the thing is does this rely on how big the stack is? Well, no, because it's only an interaction between these two pieces of data. I could make my stack really, really big, right? Just this massive linked list full of tons of different data, and it wouldn't matter, right? All I'm doing is I'm doing an interaction between the first 2 parts of the stack. And so it's a fixed amount of operations regardless of how big my stack is. And so what that means is that this is going to be running in big O of 1 time, right? It's a fixed amount of operations regardless of the inputs. For this next one here, it says, given a collection of numbers, the operation we're doing is finding the average of the numbers. Okay, so let's say I did 6, 5, and 8. Okay, so the way we find the average of these numbers is we add them up, and then we divide by how many there are, which is 3, right? So we do 6 plus 5 plus 8, which is 19 divided by 3. Yeah, we can just leave it like that if we want. But let's say I had more numbers, right? Well, to find this average, I need to add up all those different numbers, so that's more operations, right? Kind of the amount of operations will depend on how many numbers we have, and we have 6 in total. And if you do the math, you'll see this works out to 10 over 3. But the point is that there are more operations, right? There's kind of the amount of operations depends on the amount of inputs or the amount of numbers or the amount of data that we're working with. And because it's not fixed, that means this has to run in big O of n time, not big O of 1 time. All right, so what about this one? Given an unsorted collection of numbers, we want to find the biggest number. Okay, so we've got, a collection of numbers and they're not necessarily in any order, right? So how do we find the biggest number? Well, the way we would have to do this is we kind of have to compare all of the numbers to each other, right? So we take the first one and then we see, okay, it's not bigger than 3, so 3 is kind of our new biggest. And then we go over, okay, it's not bigger than 10, so 10 is our new biggest. 10 still wins to the 5, 10 still wins to the 0, and 10 still wins to the 3. But the point is that we have to kind of check every single one of these numbers, right? So that's probably an indication this is going to happen in big O of n time, right? So here we had to make 5 different comparisons. Whereas if this was all the data I had, I would only need to make one comparison, right? I just compare the 1 to the 0, and so there would be less comparisons. But the more data you have, the more comparisons you need to do, so it isn't just a fixed amount of steps. So this would occur in big O of n time. What about if I asked you the same thing, but now the collection is sorted from biggest to smallest? So we already know ahead of time that the collection is going to have the biggest at the very start. Well, if that's the case, then all we need to do is just check the start, and we don't need to do any comparisons. We just immediately know that the start is going to be the biggest. And since that's the case, there's only one operation in every kind of list that we're given. So even if I have a list of like hundreds and hundreds of numbers, that's fine because I know the first one is going to be the biggest, right? Because it's sorted. So this is going to be just one step of just looking at what the first number is. And so that is going to occur in big O of 1 time.
Question 4.
Okay, we're almost done here. We have a few different parts to it. So the first part says, how can we use stack operations to figure out how many pieces of data are in the stack? So we have some sort of stack, right? And we don't necessarily know how many pieces of data are in it. Obviously, I can just count 1, 2, 3 when I look at this, or maybe more. But the computer, it doesn't really have this picture, right? It just has these pieces of data in storage with pointers to each other. So what would be a process we could use to get the computer to actually count how many pieces of data are in the stack? And it's asking us to use stack operations to do this. Well, we have 2 operations. We have popping and we have pushing. If I push onto the stack, do you think we can use that in any way to figure out what's already in the stack? Not really, right? We're just adding to the stack. It's not helping us. But what we can do is if we pop, well, every time we pop, that's kind of one piece of data that used to be in the stack, right? And so let's say I do this stack here. I could pop and then pop and then pop, and I can do this 5 times before the stack is empty, right? And so if you just count how many times you can pop until you hit an empty stack, well, that'll tell you how many pieces of data are in the stack, right? If the stack has 27 pieces of data, I'm only going to be able to pop 27 times before the stack gets empty. So you can use this to figure out how many pieces of data are in the stack. For part A, the method is going to be count how many times you can pop before the stack is empty. So now that we have that, let's look at part B. So the method we used in part A says it should be running in big O of n time. So why do you think that's the case? Well, it depends on the amount of data we're using, right? If our stack has tons and tons of pieces of data inside of it, then, well, we're popping every single one of those pieces of data. So the amount of operations we're doing is directly dependent on how much data we have, right? If I have only 3 pieces of data, I only need to pop 3 times to figure out the size of the stack. So it's not the same amount of pops that we're doing for every size of stack. It's a different amount. So that means this is going to run in big O of n time. So a justification we could write is it's big O of n because the amount of pops that we do depends directly on the stack size because, well, we're popping everything in the stack, right? Okay, so that's part A and part B, but this seems like an expensive operation, especially, just to look at how big a stack is. Is there a nicer way to do this where it's less expensive on our computer? If I have a stack that's got 1 million pieces of data in it, does my computer really have to do 1 million operations just to tell me that it's that big? Or can we do it a little more efficiently? That's what question C is asking us to do. So can you think of a way that we might be able to find the stack size? And I'll give you a hint. You might have to modify how the stack actually works, how you actually add things to the stack in order to get this. All right, so how can we do this? So what we can do is we can sort of start a counter. And whenever we push data onto the stack, we add 1 to the counter. And whenever we pop off the stack, we subtract 1 from the counter. And it's actually as simple as that. So remember, whenever we pushed, we had several things that we did, right? So whenever I pushed some data onto the stack, what I did first is I added a pointer to connect it to the stack. And then I relabeled the top. And now we're just doing one extra step of adding 1 to the counter. So +1 to counter. And then if we pop, right, so now let's say we do a popping operation. Well, okay, that does a few things. First of all, it relabels the top. So now this is the top here, and this is no longer the top. Then it removes the pointer so that this previous top is no longer attached to the list, right? And then all we're doing is we're going to subtract 1 from the counter, right? Because this is no longer adding to our count. And so we see that pushing and popping, they kind of remain these simple operations, but we just add this extra step of adding and subtracting from the counter. Then what that does is it allows us to kind of just keep track of the counter. So when we want to know the size, we simply just ask the computer what the value of our counter is. And it'll tell us, maybe it's 7, and that means there's 7 pieces of data in the stack. And it doesn't have to actually go through backwards to the stack and find everything, because we've been kind of keeping track of it as we build the stack.
Concluding thoughts.
Okay, so that's going to do it for today. It was a bit of a longer one, but I still hope you found it useful, and now you're hopefully feeling really comfortable with how all of these stack operations work. We got a lot of practice kind of with different applications of them. We now really understand the visual aspect of kind of how these linked lists work with stacks. So that's going to do it for me today. Let me know if you have any questions or comments. But until the next video, you have a good one, you stay groovy, and I'll see you in that next Maths video.
Maths.